the following items, and you can think that's the sequence of steps for doing the application acceleration. So first we will start with the system level design, and then we have the first application code develop. Then we have to verify the design first, and then we start doing the synthesis. Okay, and then with the first working application source code, we can do the very much the initial design. And the initial design, basically you have to cover the I/O, okay, and then get the preliminary or baseline performance, okay. And then based on that, we start doing the performance design. And in the performance design, I'm more focused on the throughput, okay. And the next step is reduce the latency. I believe you all know the difference between the throughput and latency. And for system level design, we should more focus on the throughput instead of the latency. Okay. And then in the last step is the improve the area. Okay. And area I put at the last because the FPGA already give you a resource. Okay, as long as you configure your design into the FPGA resource, then there's no need to optimize the area unless you want to squeeze more performance and use more parallelism. Then you have to use your resource carefully. Okay, and at the last I will cover the host. So optimize host basically is optimize the overall application performance. Okay, so this the steps for doing the application acceleration. So let's start from the system analysis. Okay, so before that, I believe you all familiar with this computational model. Okay, and so originally you have the application program run in the CPU, and later on you identify some kernel function that could be accelerated, and then you move to FPGA part. So to doing that, the red curve here shows the necessary data movement. Okay, and so the data has to move from the host memory to global memory. Okay, and then move the global memory to the on-chip memory, and such that that can be compute by the accelerated functions. When you get the result, you save back to the global memory and use the DMA to return the data to host memory so that the application program can take the result data and proceed. Okay, so for all those data movement, there are latency introduced. Okay, and there is a I/O bus introduced for PCI accelerator card is a PCI bus. So with the MPSoC chip, the PS side communicates PL through certain selected AXI bus. So they are all the data has to move across limited bandwidth. So that's a lot of system design issue involved here. Okay, so keep in mind that there are steps to move the data in order to get the data computed. Okay, in here I identify some general guideline on system performance. So when you start doing the application acceleration, think of those issues first. Okay, first you have to think of a throughput, not just the latency. Okay, some of the application really don't care the latency. And most of the application do not care about latency. They care about throughput. Okay, and remember the Amdahl law. Okay, I will explain that later. Okay, and And then you have to identify what part of a function that could be accelerated. Okay. You have to focus on that's a larger compute bound, not a memory bound type of application. Okay. For memory bound application, once you move the computation to the FPGA side, you know that you also have to move a lot of data from host memory to the global memory. Okay, so you have to ask yourself whether it's worthwhile to do that. Okay, and also make sure the function you accelerated do not need the frequent synchronization with the host. Okay, yeah, because all the synchronization is overhead and it create latency. Okay, and then you have to pay attention to some other system overhead. I will explain that later. And in here, I will refer you the UG 1394 Chapter 4. The title of that chapter is a methodology for accelerating application with the BT software platform. So it's a very good reading that you should spend time read it. Okay. So this identify the area to improve throughput. There are basically three areas. Okay. And originally the function 2 is running on the CPU. So once you move the function 2 to the FPGA side, that there are few overhead introduced. First, you need to do the initialization through the API. So there is an overhead on the PC API function call. And you need to move data to the global memory. And the function to resolve have to return back and through the API to go back to the host CPU. And here there are three areas you have to optimize. So first area is you need to reduce the CPU idle time because that's the flow of operation from function 1, function 2, and function 3. So once you move the function 2 to FPGA side, so uh, the CPU is free from the computation of function 2. So make sure you can utilize this time slot. Okay, either fill in the pipeline operation or jump to the other thread of operations. So don't make the CPU idle here. Okay, and the second optimization, of course, is the accelerated function. So you have to customize the data path for best performance. So you try to reduce the computation time here. And also, in FPGA, there are the function, the kernel function. So you need to maximize the kernel utilization. Okay. So there are two computation resources. One is CPU and one is FPGA. So make sure those two computation resources are fully utilized. Don't make them idle. Okay. Okay. And then let's see. So next question is, once you identify the function to do the acceleration, so ask yourself, what's the best case that you can speed up? Okay. So when you do the calculation, don't forget you have to consider the overall performance. So you have to consider n actually is end-to-end performance. Okay. For example, if that's a service you offer on the through the internet, okay, then the internet or through the actually through the network, if it is a network service, then make sure your service request comes in until the request return. Okay, so this is the end-to-end performance, not just the FPGA uh, accelerated function, not just this part. Okay, so you have to consider the whole application path. So that includes the housekeeping task, including you set up the accelerated function, including the doing all kind of a synchronization between kernels and the data transfer. And also, you have to consider storage and network I/O. As I said, this application is on the network and end-to-end, so you have to start from the network side. And the data, if coming from storage, okay, so make sure you also consider the storage access time. Okay, so the first thing, yeah, think of the end-to-end performance. So, and then you have to run the profile too to identify the bottleneck. Okay. And the underload says is a very simple equation that if only a fraction f of the whole application can be parallelized by a factor p, so the whole throughput, okay, so this part is a non-accelerated part, and this part is a accelerated part. Okay. Then the whole speed up like this. So even though you can make the parallelization is infinity, the maximum you can speed up is this equation. Okay. So in the case that the whole accelerated function occupy only 50% of a total computation or total application time, so you know the maximum you can speed up is 2x speed up. Okay. No matter how acceleration HS part you can be accelerated. Yeah. So I remember a few years ago, Microsoft published a paper. They first introduced the APG acceleration in their bin search. And in the paper, he talked about all kind of optimization and claimed that the searching engine can be speed up two orders speed up. That means over 100 times speed up. However, in the final in the paper at the end, you say the whole system only speed up 2 times. Okay, so you can think that. So actually, I think that that paper is quite honest. He tell about the total system. So I believe they have a lot of work to speed up their bin search engines. Yeah. Okay. Okay. Let's talk about first thing that. So first, we talk about you have to target the large and computer bound task. Okay. So, so that's a typical. I just talk about that. There are some data movement here. Okay, so including the API function call and the data move over the PCIe bus and the computation run on the FPGA. Okay, and so let's focus on these two parts. Okay, the PCIe and FPGA. Okay, sometimes you have to identify this problem is a compute bound or I/O bound. Okay, since the data has to move through a limited bandwidth, the I/O bus. So sometimes the I/O is the bottleneck. Okay, as we know that the FPGA side there are a lot of computing elements. For example, for FPGA, the big FPGA has over 10K DSP. Okay, and for 10K DSP, each DSP supposed running at 300 megahertz. Each DSP take 3 operand. Okay, that basically is a multiplication A times B plus C, 3 operand, and each operand is let's say it's 32 bit, 4 byte. Okay, so that's a total 12 byte. Okay, and then so you need the data. How much total data bandwidth you need? There will be 10K times the 300 megahertz times 12 bytes. Okay. So that will be wow, that be 36 terabyte bandwidth, right? Am I calculate right? That's three older three. That's six older. Okay, and that's another three older. Okay, giga. Yeah, that will be 36 terabyte. Yeah. So in this case, that the the I/O will be memory bandwidth will be a bottleneck. Okay. So you have to use all kind of optimization. For example, the caching, these things to try to minimize the I/O or memory bound. Okay, to increase the operation density. Okay. And so the best application that can be accelerated is you have only small set of data and you're doing iterative computation on the small set of data. I think that's the idea. However, in today's application, there are a lot of application needs big data, like machine learning that need big data. Yeah. So things get very complicated. And you will find out when you're doing the HLS design, a lot of time you will think of how you can move data efficiently. Okay, there are all kind of techniques for you to do that. Okay, and again, I have to repeatedly mention that you have to pay attention to the whole system workflow. Okay, you have to consider storage and network into the pictures, and and the data transfer among the network. For example, the data moving around the storage, the CPU and accelerators. Okay, in here, you will try to use the techniques peer-to-peer transfer. Okay, for example, a lot of time the storage is hooked on a PCIe bus. Okay, and you have the accelerator FPGA also put into the PCIe bus. Okay, so the computation actually work on the data from storage. So typical, you will move the data to DDR memory first, and then you move the data from DDR memory to PCIe. So for this data movement, it's not only uh, introduce actual latency and also create a lot of use a lot of power. So in here, the peer-to-peer transfer, I mean, you should be able to move data directly from storage to the FPGA. Okay, so that's the peer-to-peer transfer. To do that, today in current OS, Linux OS, they support the peer-to-peer transfer. So try to use that feature possible. And also, if you want to directly work on the data set in the storage, then you will run into a problem that's the data format mismatch. Okay, so the data stored in the storage is not readily computed by the FPGA. So oftenly, so the CPU, why people move the data to have the CPU involved in data movement, uh, because the CPU will do the data format, okay, and then to feed into the FPGA. So for doing the peer-to-peer transfer, before your acceleration function, you will need a certain data format function. Okay, streaming the data and extract the necessary data to feed into your accelerator. Okay, so there is a data format issues. Another issue is we know if the data has to go through the DDR memory, And the memory, system memory is manipulated by the operating system and shared by many threads of processes. So the memory management could not allocate a big chunk of memory for you. So most likely those data are scattered in the system memory. So you have to scatter and gather the data, okay, into one continuous uh, memory and then move to the FPGA. So in that case, they introduce actual data movement for scatter data, and you try to gather together. Okay, so you will see there really has a lot of system inefficiency here. Okay, so for doing all those data movement and the acceleration, you have to set up initialize. And when doing the task operations, there are often event synchronizations. Okay, so in here, a more advanced design techniques is try to compute on the fly. Okay, like a data flow. Now in today's compute architecture is store and forward. So like this case, you move the storage data to FPGA. So you have to store into the DDR system memory and then forward to the computing FPGA device. So in today's, because the store and forward is a much easy approach, although it's very inefficient. Okay. So for compute on the fly, you want to do the data flow, compute the data while the data is moved. For example, for the network surface, if that's the network surface, maybe I don't know whether you guys know the NVMe over TCP. Okay. So suppose you have a network storage. That's a network storage. Okay. Normally the storage is hooked on a PC and use the PC to connect to the network. Okay. So the traditional way is the NVMe protocol going through the NVMe CPU, doing all the required processing and set up the NVMe device and get the data to the DDR memory and then call the network surface to move data to the network. So the industry introduced the NVMe TCP protocol so that the and then you use the network and storage PCIe peer-to-peer transfer, set direct transfer channels between the network and the storage. So this command directly take by the storage device and process it, and then he move the data directly to the network. Yeah. Okay. So for doing that, this chipset or the PCB the motherboard need to have a capability to do the PCIe peer-to-peer transfer. Okay. And so if so another technique you try to write the software in a pipeline way so that you can try to hide in the overhead. So you have all those data movement. However, you can schedule them in a pipeline way so that those transfer, the latency for the transfer is hidden. Okay, yeah. So in here, I talk a lot about the system design issues that hopefully you can get uh, some idea about it. Okay, so here is pretty much for the whole system design. Yeah. And then next step, once you have the application, Once you have the application ready, that first step you need to verify the design. Okay, I'm very emphasized on the verifications for for the new engineer on board. For design engineer first join a company, and they will receive 6 months of verification training. I think I always believe verification techniques is the foundation for all of the design skills. Yeah, without good master of a verification skill, then you could not design, you could not do the advanced design. Okay, so you can imagine how can you design something and you don't know how to verify it? Yeah. So doing the system verification is a very important technique. Yeah. So here I write down a few guidelines that for you to write a test bench. Yeah. First, you separate the kernel function from the test bench. Yeah. So try to do good partition here. And the way you do the partition will, because there are a sequence of steps to doing the verification. You have a C, you have the, imagine you have the C verification, C simulation, okay? And then you have a code simulation. And then when you hook on in the system, that you have the system, in-system verification, okay? So you have all different level of verifications or system validations. Then you want to write the test bench in a way that can be used in the future in the following steps. Okay. Um, okay. And then the system level integrated test is very important. Yeah. So often, hmm, what happened? Oh, here. No. Okay. So here I raise the question that the test bench you develop, can it be integrated into application body? Okay, remember that even though you have done all the detailed verification or even the in-system validations, but however, when the application program really go online and doing the test, so the application program could fail during unforeseeable test. You don't know how people going to use your application, and you don't know the system loading. Okay, it could be under very stressful stress the system test. So if it's fail in the field in the system, then how could you debug? Okay, so a good design that always have to think that how you can debug the program from the very beginning. So when you develop the test bench, and you probably need to think how the test bench or part of the test bench can be integrated into the application body. Okay, so that the system when it's running, you can monitor and then dump certain trace information for you to do the system debugging. Yeah. By the design, very important is the test coverage. So you have to make sure all aspect of the function is fully verified. Okay, so you have to check the code coverage. Yeah, and I remember a student doing a design, and then he tried to run the code coverage. He reports that there's nothing you can, not no information from the code coverage. Okay, that's because currently the application code you deal with is a very simple case. So there is no much branch, and then a lot of corner cases you don't run into it. But a real complicated application program that the code coverage to validate the function of the application program um is a very tedious process. And code coverage always is the first step to ensure your application quality. Yeah. So for doing the hardware, you have to make sure, for example, here the test bench you develop do cover the FIFO full empty case, and make sure your I/O latency you have a random I/O latency. Okay. Uh, you may have a very short latency and also need to test for very long latency, so that you can stress the case like the FIFO empty full. And then if your code has many branch conditions, make sure every branch is pass is verified. Okay, so the code coverage is also very important. It's very important. Yeah, and you want to use the same test bench to do the C and RTL code simulations. So at this stage, okay, for C simulation, you only verify is the function. You could not verify the function, the performance. Okay, and you can use the CRTL code simulation because the kernel function is already synthesized, so it's run with the real hardware. So the kernel function will be cycle accurate. So you can verify the kernel performance, especially is the II and its latency. So you use the code simulation to verify the II and latency. Yeah. Okay. And then when you develop the test bench, make sure you do the auto check for correctness. Yeah. Okay. And then okay, another advice I will give to you is always embed some test debugging feature in the system workflow with a minimum overhead. Okay. Um, so when the application code pull online uh, and running in systems, and you need to put in some debugging features to save some very critical information. Always monitor critical information or indicator or some kind of indicators. Okay, so when the application code crash, for example, when it's a crash, then you need to be able to extract the indicator information out for you to do the preliminary debugging. Yeah, and oftentimes that the fail case may not happen all the time. Maybe it happen intermittently. That's a very troublesome situation. Yeah, and if you design with the debugging in mind from the very start, then can save you from many crises. Yeah. Okay. So in here, I list a few critical things. Oh, yeah. So for those things, it's good, but you may not have an idea how you do that. But don't worry about it. So once you get a real work to do, think about these things, and then try to put those practice those in your design. Okay. So that's a CRTL code simulation. Yeah, the mechanism is very simple. First, for the typical C simulation, is used to prepare the input data. Okay, and then you kick out the test bench, which is the kernel function. And for the kernel function, you take the input vector and generate the output vector. And the third step is you have to do the post simulation check-ins. Okay, so to do the code simulation and critical issues, you have to make sure you provide sufficient FIFO depth to avoid stall. Okay, so I believe some of you may have experience uh, that stall, the whole simulation stall. Yeah, so most likely it's because of these issues. And for some of the optimization that could not be supported for code simulations. Yeah. For example, Reshape on the array argument. For this kind of optimization, that could not be supported in the code simulation. Yeah. And if you run the data flow, sometimes you will run into deadlock case. If a deadlock happens, then you can use a waveform viewer, okay, to do the debugging. And in here, I especially emphasize at the synthesized design stage. Normally, we use the directive of pragma to guide the AAHLS optimization. Yeah. So we will try to minimize to restructure the code to meet the performance. I know many of you have the RTL design experience. So in the very beginning, when you write the C code, you are writing the C code in a way that very much like the RTL design. Okay, and it's you should not do the coding in this way. Okay, you should try to do the normal C plus coding style. Okay, and then try to use the directive and pragma to guide the AAHLS optimization. The benefit for doing that is you can leverage the compiler optimization in the future. Okay, if you write the code in a fixed way that the future compiler could not do better work for you. Okay, so first try to you simply use the directive and pragma. Okay, and then and you do the synthesis. You have to after that you will study the synthesis summary report. Okay, and then see whether it meets your design targets in terms of resource and performance. Okay, and then I also recommend you to study the schedule viewer, property viewer, and data flow viewer to analyze the data path and control flow. And another important thing is here. I believe most of you don't really study the synthesis log file. Okay, so in here, that's a very brief list of synthesis log message. It actually contains many information. In, it includes the synthesis steps and then the checking status and optimization result. Okay, so oftentimes you can find the clue why your code does not perform well. Okay, so if you study the log file frequently, that you will gradually build up your experience in the high-level synthesis. Yeah. So in here, I very much recommend you do review the synthesis log file. Okay, and then next we talk about the interface best practice. Okay. All I say here is a very important guideline that you will try to follow those steps in doing your application acceleration design. Okay. For the interface practice, first, you want to separate I/O access from the compute. That's very, very important. Okay, because the I/O and compute optimization may take a different strategies, especially from I/O and compute. First, those two has a different optimization strategy, and oftentimes in between you will have some kind of cache structure in between. Okay, so if you are coding, for example, if you write code in this way, okay, then you're actually doing the I/O and the computation intermix. You intermix the I/O and compute. It's very hard to do the optimization in this way. Okay, so in here we want to do the like that's the data output. Okay, so you decouple the input output assets from the compute. Okay, so in here you can do all kind of memory. For example, for this I/O, if it deal with the memory or deal with the PCIe or any of the external storage, they have a different optimization strategy here. Okay, for doing memory, you can have a wider bandwidth. You could have a multiple bank. For doing the PCIe, you can have a or XI bus. You can have a different bursting techniques. Okay, so once you write the code in this way, then it's hard. So you do that and put into a local buffer. So there's a cache mechanism here. Okay, so that's the reason write the code to separate the I/O access from your compute. Okay, so for I/O, then depends on the characteristic of the I/O bus. And for PCIe or XI bus, you try to do the burst transfer. Okay, for doing the burst transfer, then you need to have a local buffer. You need to have a local buffer. Okay, and then you may have a different concurrence access memory pool. Okay, so if you separate I/O, then it's transparent from your computation. Your computation, you don't need to care about where the data coming from. The data could be from different memory pool or from internal cache or whatever. Yeah. Okay. So for I/O, you try to do the burst. And for people familiar with the C programming, use a lot of pointers. Okay. And to tell the truth, that pointer is really not friendly, not the HES compiler friendly. I will introduce it later. Yeah, simply because in C code, people use pointer for pointer aliasing. Okay, and people use the pointer too free. Yeah, then it create a lot of trouble for the HES compiler. So in this case, the compiler could not pipeline the loop. Okay, so you have to use pointer with cautious. Yeah, must be very careful. Yeah. And you want to use a wider I/O bus, like the on-chip memory provide 512 bits memory data width. Okay, to fully use this 512 bit data width, you try to use the vector data type. Okay, and also we encourage you to use the streaming, especially streaming with vector. Yeah. Okay. The streaming is good because for streaming or data flow, you don't use the data buffer. It doesn't like bus transfer. Okay, bus transfer, then you will need a local buffer. Okay, so here I list a few very key message about the interface best practice. Okay, here let's talk about the pointer interface. Okay, and make sure you use the pointer on the interface, and that is read or written once per function call. Okay, if you use the multiple assets, the pointer uses multiple assets, then you'd better use a string. Okay, so if it's multiple assets, that make sure compiler does not optimize a way to prevent the compiler to do the optimization on the multiple assets. So you have to declare as a volatile. Yeah, and you have to make sure its correctness by doing the code simulation. For these examples, this pointer is used multiple times. Then you have to use a volatile. Okay. Otherwise, the compiler will optimize away. Yeah, remove some of the operation here. Okay. And then you try to avoid pointer arithmetics. It's better you use an array with the index. For example, in here, that's a pointer, okay, and then you are doing the arithmetic on the pointers, okay. So in this case, then it's better to use the array with the index, using index to access. It gives you it's more HS friendly to do this way. Okay. So for memory interface, you try to maximize the memory bandwidth because the FPGA already have those bus widths allocated for you. So you'd better just use those bandwidths. And FPGA already provide the multiple memory ports. Okay, so you can use a multiple memory port. In the HLS, you use the bundle syntax to specify different memory ports, and you can increase the memory port width to 512 bits. Yeah. To do that, you can use a vector for SIMD. That's the data parallelism. Yeah. You increase the data width, yeah, to do the data parallelism. And you want to minimize the rewrite on the I/O port. Okay. If you have to do the multiple rewrite access, then you'd better to cache the data. Okay, instead of every time you access the I/O. Okay, and you do the rewrite by burst. To do the burst, you use a pipeline and make sure the for loop with the pipeline, you don't put any conditional statement because the conditional statement prevent the bursting. Yeah. And if you have the multiple access, as I said, that the read data, you try to read once and use a local cache for data reuse. Yeah. So this the example we have introduced before. You declare a vector data type, and in here that's the 32-bit integer with a vector size 16. So this give you 512 bits data width. Okay, and then there's a XI interface, and you in here also demonstrate you can use a different memory port with the bundle set to a different name. Okay, then you will allocate different memory port. Okay. Okay, so for memory access, it going through the HI interconnect and to the memory controller and reach to the memory. So it takes a latency. Okay, the latency is no fixed latency here. That's a system dependent, and also depend on if there are other thread of operation going on. Okay. So you can specify latency, but the latency here is specify the latency simply for the simulation purpose to estimate your performance. Yeah. So in order to optimize the performance of the memory bandwidth, there are two factors you need to consider. One is the burst length. One is the number of outstanding requests. Okay, so how do you decide these two parameters? I believe the HLS, the code simulation, the new VTIS tool, they will decide it for you. Yeah, from the code simulation, the code sim, they can figure out optimized value for you. For a very simple rule to define the reburst and the number of outstanding is, let's say that you have a latency, a round trip latency. What I mean round trip latency is from the request issue to the data return. Okay, they give you a latency. And then, so let's say that you have a burst 16. That means you have a 16 data in burst. Okay. It also depends on the data width, the width. Okay. Yeah. Then if you have 16 data, so let's say the 16 data takes a certain duration on the total latency. Okay. And then so how many real outstanding requests you need to fill up the total latency? Okay, so then you can divide the latency by the time for the burst transfer, for a request burst transfer. Okay, then you can calculate. So if you have a longer burst, every time you have a longer burst, then you can have a less of a outstanding request. Okay, so this is a very basic rule of thumb to calculate the burst length and the outstanding. And the burst length depends on your data bus width. So that's pretty much given by your design. And number of outstanding that depend on the latency. Okay, and the latency is the system dependent. So in order to get a more accurate estimation of the latency is you try to do a simple rewrite and to calculate the latency. Yeah, the latency will be most likely is a distributions. Okay, so you want to choose a reasonable latency. You really don't want to choose for example, I want to cover 99% of the latency. Then it may not be reasonable because they may have sometime due to other event, it may take a very long latency. So choose the right latency, the latency wisely, so that it won't consume too much your resource. I think that the best interface practice is user streaming because streaming gives you many benefits. First, it doesn't need buffers. Okay, it uses a simple FIFO to do the transfer. Okay, and second, the benefit is low latency. Okay, because using the streaming, you don't need to fill out the buffer. Since no buffer, so you don't need to wait for the buffer fully fill before you process it. And also you don't need to wait the previous loop or task complete. And then you can start process. Okay. So streaming is I would suggest you always use streaming. Okay. And once you impose a streaming that you will try to figure out how to fit your coding, fit your design within the streaming paradigm. Okay, so always start with the streaming interface in mind and try to adjust your code to fit into the streaming. Yeah, that will give you the best and optimized design. Okay, so for streaming, you also consider uh, using the vector. That means you consider SIMD. Yeah, and there's no need for local memory buffers. Yeah, and make sure the streaming can be stored, okay, from upstream or downstream. So the II value actually is varied, okay, but it should be approximately equal 1. Okay, so in here, it has a simple code. For example, yeah, in here, that's a 512-bit with data stream. Okay, and then you read the data in and do a computation and stream out. Okay, okay, let's talk about the memory I/O usage. Okay, so in here I'm talking about the memory from the host memory. Okay, and that's the source of the computation data from. And so we will make sure you transfer large block of data from host to global memory. Because every time you include the memory buffers, there are system overhead involved. You really don't want to transfer a small amount of data. You try to aggregate all the data and transfer the data in a big chunk. Okay. And then you try to avoid copy scatter gather because the host memory may be fragmented. Okay. And Intel provide a DPTK memory pool manager. In here, uh, because the operating system server many threads of processes, and different thread process they use a different buffer size. So when the thread allocate memory and free the memory, so that create the system memory fragmented. Yeah. So so always oftentimes they always could not allocate big chunk of the memory. So if you request a big chunk of memory, that you may find a system halt because it's doing the garbage collections. Okay. So in order to prevent that, and the Intel DPDK, that's a software package. It takes the memory management control from the operating system. So it will do its own memory management so that it can quickly allocate a big chunk of the data buffers. So that's the memory allocation may play very significant role here. Yeah, so give you a lot of advantage to use like the DPTK. Yeah, and so you don't want to copy all the data to the host. Only for the data is necessary. So for host to kernel data transfer, I will suggest using the following way with priority. First, consider using stream interface. Okay, data flow model. It provides low latency and low resource usage. And then you try to use the on-chip memory. Okay, consider using the cache and buffering techniques. Yeah, and the next one is using the global memory. Yeah. For example, in here, the host or kernel, if the kernel to kernel transfer, okay, you use a string, that's the first priority. Or use the on-chip memory, on-chip memory. The or use the next use the global memory. Okay, the kernel transfer data to the global memory and then global memory to the next kernel. And the worst one, oh, you should never use the host memory to communicate the data between two kernel functions. Okay, so that's my recommendation to do the host kernel to kernel data transfer. Okay, next let's talk about the performance optimization. In here, I mainly focus on the loop optimization because that's the major targets in most of the application accelerations. Okay, yeah, for performance optimization, there are three optimization goals. Actually, there are three methods, three things that you have to consider. First, you use a pipeline and with II equal 1. Okay, pipeline is a way of task parallelism. Yeah. So you have to make sure all the pipeline, all the tasks run at the maximum throughput. Yeah. Um, this statement is not exactly correct. I should write this statement as you try to balance. Okay, balance all stage of the task. Yeah. You should balance, not always maximize. For example, you have a task level pipeline going through several tasks, T1, T2, and T3. Okay, so this guy could give you only II equal 2, and it makes no sense you optimize this II equal 1 and this one II equal 1, right? Yeah. So you find these things that you have to first focus on this one. Try to push this to II equal 1. Yeah. Or this 2, and this 5, then you focus on 5. Instead of you work so hard to put this equal 1. Yeah, this makes no sense. Yeah, because the whole throughput is still II equal 5. Yeah. So so ensure all the pipeline run at balanced throughput. Should put this way. Yeah. Yeah, of course, you try to push every stage is I equal 1. Yeah. Okay, so that's the first thing we will talk about. And the second, you try to consider the data parallelism. So that's the scaling and folding, the SIMD. In order to meet these two requirements, you have to consider optimize the memory efficiency. Okay. So if this is a compute bound problem, you should saturate the pipeline with data from memory. Okay, and then if it's a memory bound, then you focus on try to maximize the bandwidth and utilization. Okay, so it depends on your problem. Oh, it's if the compute is compute bound, then while you push the compute bound, the data is enough for you to saturate the pipeline. Then there is no need you continue push the memory bandwidth and utilization, because when you increase the memory bandwidth, you also increase the resource usage. Yeah, if a compute bound, you just need enough data make to saturate pipeline, that will be enough. If you know that's a memory bound, then you focus on improve the memory bandwidth and utilization. Yeah. So remember that when doing the system optimization, there are so many factors. Okay. So you have to identify which factor is play the most dominant role, and then you focus on that. Okay. After you fix that problem, then the dominant role may change to other topics, and then you work on the other one. So you have to choose the dominant factor, wisely choose the dominant factor, and don't spend your effort on something less important. Okay, that's a very, very important. So that's why the experience in doing the system analysis, and you have to base on a lot of report, and Pratice too provide a lot of reports. You need to develop a methodology to analyze those reports, and from those reports to identify the critical factors, and then you work on that. And remember, that's always a iterative process. Yeah, when you fix that problem, another problem become dominant, and then you work on the other one, and then gradually that you get more optimized system. Yeah, by this kind of iteration. Okay, and so that's a very basic concept. Okay, latency and the initial the II. Okay, why I introduce because that plays a guidance for your optimization. First, we all know the II, that's the initial interval. And for one iteration, there is a iteration latency. Okay, and there's a loop. There's a loop latency. And if you process n inputs, then you can get the loop latency with this equation. Okay, so that's the loop iteration latency, and that's the II, and that's n input. So for this equation, so if n the input data is much larger than the latency, okay, in this case, you can ignore this term, the latency. Okay, so that's why that oftentimes the latency is not critical as long as you have a lot of data input. The iteration latency is not the issue. Okay, so from here we know I equal 1 is the ultimate goal. Okay, yeah. And this you all know the pipeline and the data flow. Okay, and pipeline you have to finish one function before you pipeline next function. And for data flow, as long as you produce one data output, and next stage your function can proceed. Okay, so for data flow you get less latency. Okay, and yeah, compared to the pipeline. Yeah. Okay. Okay, so here there is a subtle difference between the function and loop. Okay, for a function, you may have many you may have a sequence of a loop. Okay, so you can return in this way, or you can write, you can put each loop into a function. Each loop becomes a function. Function A and function B and function C. And you call function A, function B, and function C. Okay, when you write the C code either in this way or in this way, actually the compiler synthesis perform differently and the performance is different. And the resource usage is different too. Okay, so for a pipeline function, okay, if the function you put a pipeline here, okay, if a function for a pipeline function, the function run forever and never ends. So that means that the function is automatically rewind. Okay, and then for this function, if you put the pipeline here, it will enroll all the loop in the function bodies. So in this case, that you really should use the data flow. Okay, so function, if you have a multiple loop here, and you put a pipeline here. So in this case, it will enroll all the loop, then it will consume a lot of resource. So in this case, we really like to use the data flow. But if you use the data flow, all the loop must be written in a way that can fit into the data flow model. Okay. So that's a pipeline function. Then if you pipeline a loop, then it's an issue that the loop complete all operation before starting the next loop. Okay, for example here, yeah, if you have a multiple loop here, okay, for this loop, you have to complete it, you pipeline this loop, okay, the loop is pipeline, but the next loop start must wait for the previous loop, complete. So you will see there is the gap here. Okay, there's an idle here. So HLS provide a loop rewind function. The HLS directive loop rewind. So that with the loop rewind, that you will move the loop initialization in front, so that you can start next loop earlier. Okay. But function, pipeline function, then it doesn't need to do that because the function is automatic rewind. Yeah. So that's the difference between the function and loop pipeline. Okay. So here, this diagram, this page is quite important. That how you develop the code using the pipeline data flow. Okay. So in here, so that's a function definition. Inside this function, you have a sequence of either pipeline loop or function, pipeline loop or function. Okay, and you want to use a data flow on it. So let's say you do the pipeline to function and loop. Okay, okay. Let's look at this. First, let's take a basically, as I said, in here, if you pull a pipeline here, okay, you can pipeline the function, but if there's a multiple loop here, then you will enroll all the loops. Yeah, so it's better use a data flow. Okay, and so you use a data flow here. All this will work in parallel. Okay, so in here that could be the function. So all the function will work in parallel. And also, if there's a loop, and the loop has to be pipeline. Okay, So in here, you have a loop, another loop one, and there's a if a loop two. Okay. So for each loop, you have to use a pipeline. So must be a pipeline loop function inside the data flow. Okay. So to do these things, I suggest that you work from the bottom up. Okay. So you have a sub function. Those are the sub functions. Okay. So first you have to work on the sub function. You try to pipeline the sub function first. Okay. And then you try to pipeline a function contain the sub loop. Okay. If a pipeline a function with a sub loop, then you may enroll all the loop in the hierarchy below. So in that case, then instead of pipeline the function, if there's a function, what this statement says here is a function. If you have a loop, okay, you put the pipeline here. Okay, it's basically you enroll all the loop. So you want to pipeline put into the loop in the one hierarchy below. Okay, to avoid the enroll of this loop. Okay, yeah. So you work on the sub function or sub loop first, and then going up layer use the data flow. Okay, so it's better use the data flow with a pipeline loop, and so that all the loop can operate concurrently. Yeah, and also make sure that you choose the operator. Okay, and those operator you choose the pipeline version. Okay, so you can use a resource directive for multiplier adder or block run. Okay, you can use this resource directive to do the pipeline at the operator level. Okay, so this give you a high level framework to apply the pipeline or data flow, yeah, in a function construction, function and the loop construction. Okay. Okay. Next, we work on more detail that how we do the pipeline. There are issues to prevent the pipeline. Now, for those things that we already talked about in previous lecture. First, we try to avoid the variable bound. And there are two important factors that prevent the pipeline. One is the data dependency. We call a loop carrier dependency. And there are three types of loop carrier dependency. And what we main focus is the read after write, and because that's the true dependency. Another thing prevent you from the pipeline is the resource limitation. Okay, so resource could be computing resource or I/O or memory resource. Okay, so we introduced how you calculate II. So subject to the two constraints. One is the resource. Another one is due to the recurrence. That's the loop carrier latency. Okay. Let's look at this equation because this equation plays very important role in the pipeline optimization. Okay, what it says is here, if an operator, this is the operator, okay, C, that will be used in the future iteration. Okay, so from the iteration to the latency to generate the C and the distance and which iteration the C variable will be used. That's the distance. For example, in here, okay, the AI plus 2, okay, will be used with 2 iteration later. Okay, so the distance is 2. Okay, so in order to optimize the II due to the loop carrier dependency, you have a 2 way to do that. Okay, one is you try to reduce the latency. Okay, the latency, how the C is calculated, and yeah, and be used for the for next iterations. Okay, you try to reduce the latency, or you try to increase the distance, right? Change the in those two that you need to restructure your code. Okay, so later on we will see the techniques to improve the II. Okay, before you really spend effort to restructure your code, first there is an easy thing to do is first remove the compiler limitation on loop carrier dependency. Because the compiler has to be very conservative to make sure the code is synthesized, is safe. Okay, so if there is anything that could not be decided at the compilation stage, that compiler has to assume the worst case. Yeah. So a lot of limitation is imposed by the compiler inefficiency. It may not be the real limitations. Okay, so first step, we try to avoid those compiler limitation. First, we try to avoid using the pointer arithmetic because the pointer makes there could be a pointer aliasing. Okay, and that's the compiler really don't know outside the scope of the code. Compiler could not know whether there is a conflict or not. Okay, so we try to avoid this kind of coding. Okay, and then for the loop, we try to use a very simple array index. What I mean the simple array index is you have a constant bound and increment by 1. Okay, for this make it much easier for the compiler. Okay, and you really need to avoid the following coding. For example, non-constant in array index. For example, this array index and k is an unknown variable. Okay, in this case, it really could not calculate from the previous one. It really cannot calculate the distance. If it could not calculate the distance, it will, the most safe one is assume it's 1. Okay, so that means the data will be used in next iteration. Okay, so it's really bad. Okay, don't do that. Compiler could not figure out. Yeah, and then the next case like a multiple index variable. Okay, like in here. Okay, the I and Z loop index variable for a double nested loop. Okay, for this, it's really the compiler has a hard time to calculate the distance of the iteration. Or there is a nonlinear indexing. Yeah, there's a loop variable and C I is a loop variable and C is a non-constant variable. You try to avoid those cases. Yeah, because compiler could not handle. Yeah. So in the case, in the next few slides, I will introduce techniques to overcome these issues, even though the code is written in this way, because maybe your algorithm just have you just have to write the code in this way. Okay. In that case, there are still other ways to get around the compiler limitation. Yeah. Okay, the next one is simple. Yeah, use the loop with constant form. Yeah. And if you really know what you are doing, and then you can simply use the HLS dependent false. Okay, and tell the compiler, just go ahead and give me II equal 1. Forget or ignore all the limitations. Okay. Okay, next I will introduce a few techniques to improve the II. Okay. So after I finish this, I will give a 5 minutes break. Yeah. Otherwise, I'm afraid that there are a lot of material here. I'm afraid you cannot consume too much material. Okay. First techniques, we have been introduced the data forwarding. Yeah. Data forwarding basically is the idea to reduce the latency, reduce distance. Okay, so originally all the result, the past result has to go to store and load path, this latency. Okay, so we use the data forwarding techniques. Basically, the result pass directly to the function unit that required it without going to the I/O stage. Okay, so that's you become this one. Okay, using a temporal variable. Okay, so basically you reduce the latency. The latency reduced to 1. Okay, yeah. So in that case, so use a temporal variable. Okay, so that's the data forwarding techniques. Yeah. So you based on this equation, you try to reduce this latency here. That's one way to do that. Okay, let's talk about another case. This case is a much more complicated. Let's say that you have a 64-bit double operation for the multiplication and add. So for this kind of a data type, the operator take a multiple cycles to complete. So this is an example of a matrix multiplication. Yeah, and you have a 3-level loop. Okay, let's focus on the inner loop here. Okay. In here, you try to do the pipeline, and then you like this to be II equal 1. But can it be IO equal 1? No, you cannot. Even though you use data forwarding, the temporary variable here. But this operation itself, since it's double, it takes a multiple cycle. Okay? It takes multiple cycles. Then how could we make this loop II equal 1? Is it possible? You can give a thought. Yeah, yeah. Remember here we already use a temporal variable here. That's a register. Okay, so no array save and load here. The operation here take a multiple cycles. Yeah. So in this case, we can still do II equal 1, but we need to have use another technique called loop transformation. Basically, using the interleave techniques. For this, I will talk about that in next. I will be to be introduced in next lecture. So that's the one case. Okay. Another another case is the speculative. Okay. Let's look at this case, this is a for loop, a loop, okay? But the loop as a condition. This as a condition, this could not finish in one cycle. Yeah. So the II cannot be less than the latency to calculate as a condition. Okay. In this case, can we make II equal 1? Yeah. Another case is the loop with the data-dependent control flow. Okay. Let's take this example. Okay. This case happened in some of the applications. Okay, let's say this is the loop. Okay, the loop as a condition x. The x depend on three functions. One is the condition function c function. C function take latency 2. And there's a slow function. Slow function take latency 3. And there's a fast function, or fast function I should say 1. Let's say 1. Okay, that's 1 here. Okay, the fast function is 1. Okay, so for compiler, then you will basically use the II equals 3. Okay, can we make II equal 1? So that's a speculative. Speculative is we always assume, for example, this equation. Okay, we always assume it's going this fast path. Okay, so in this case, you continue run IA equal 1 until 2 cycle later, and you find out the condition C is choose the slow path. Yeah. Then you try to recover, just like in the process of design, branch prediction. Yeah. You assume they always choose this path. Okay, so that you give you the II equal 1 until you find out it's wrong. It's wrong, then you have to do few things. First, you have to recover. Okay, you have to first remember the process of design. If a branch prediction you predict wrong, then you have to flush the pipeline and you need to restore the previous state. So you have to keep all the states in the middle states, and then you need to recover that. Yeah. So for this kind of code, can we restructure the code to make II equal 1? Yeah. So you have to use speculative techniques. And even though the result, if it's a side effect, for example, the path will update the external memory, because once you update the data in external memory, they'll become globally visible. What do you mean globally visible? That means other process will see the memory content. In that case, you could not recover, because you don't know how these things propagate and how much it influence or affect. Yeah. So update global memory so that other process will see it. This thing is once you reach this point, then it could not be recovered when you make the wrong speculation. Yeah. So in the second question, can we still speculative even though there is a side effect? So for these topics, I will introduce in next lecture. Okay. Another thing, we all know the HLS compiler is the II is statically scheduled. Okay. So the HLS only performs static scheduling, and oftentimes that the pipeline is dynamic. Okay, there are so the dependency actually is uncertain or non-uniform. Okay, in this case, uncertain means like that's the example we just talked about. If an index contains a variable and the variable is not known at the compiler time, okay, in that case, this kind of case happen in the matrix decomposition or triangular matrix computation. Okay, so you want to write a code that is flexible to support different applications. So the code is written in a way with a parameter, and that parameter is not determined at the compiler time. In that case, for compiler, the most conservative way is choose uh, m equal 1, the most conservative way. Yeah, yeah. So that's the case for uncertain dependency. Or the dependency, like this equation, is a non-uniform. Okay, then you could not use a fixed II. The II cannot be fixed. Okay, so those two issues could not be solved by the static scheduling techniques by the HLS compiler. Okay. So previously, I conclude few uh, the pipeline techniques. Those are pretty much quite advanced pipeline techniques. Yeah, but if you are doing the RTL design, you could use all kinds of techniques to overcome this problem. It can be very flexible. But since we are using the high-level synthesis, you have to live with the limitation of the current HS compiler. Okay, so I still want, even though you're running into this kind of conditions, I still want to write a C++ high-level code and still use the current the current HLS compiler with the limitations to achieve the optimal result we can get. Yeah, so that's the topics we should study in next lecture. Okay, in here, that's next technique is parallelized loop. We use enroll. Okay, so once you enroll multiple iteration, then you will run into either the dependency between the loop or the resource limitation. Okay, so you have to overcome that. So so that means when you enroll, you need much larger data bandwidth than you use a vector data type. Yeah, SMNT. And then you have to increase the DRAM bandwidth. Yeah. So increase the DRAM bandwidth, there are two ways. One is using the 512-bit data width or use multiple memory channels. So those are the things that techniques you will need when you enroll a loop. Okay, previously we talked about the function, the difference between function and loop. Okay, so one key thing you have to know is the function actually execute concurrently, but the loop execute sequentially. Yeah, so in this example, you try to enroll So when you enroll, you actually instantiate multiple loop. Okay, but those loop are executed sequentially. Okay, so it doesn't give you much benefit here. But for function, if you change to a function and you do the enroll, so all the function will run concurrently. Yeah. So that already explained that in previously. Okay, here then how to you execute multiple loop in parallel. Okay, one technique is using loop merge. Okay, so that's one technique. Yeah, you put a multiple loop merge into one loop, so those operation will run concurrently. That's one method. Okay, or you can use run sequential loop, but in a pipeline manner using the function by creating a function. So you put each loop into a function, and then you call the loop functions. That's the second way to do that. Okay. Another way is data flow on loop. You put the data flow here. Okay. So in this case, this loop will run concurrently. But there is for the data flow, you have a very strict coding that you have to pay attention to. Okay, I will explain that later. Yeah, actually, that's in my previous lectures uh, before. Yeah, so there are three ways to run multiple loop in parallel. Okay, okay, let's talk about data flow. Okay, there are two standard form, canonical form. Okay, one is for function. Okay, that's the basic coding. You follow this coding style, okay, to do the function data flow. Okay, so for those functions you do the data flow, make sure those functions cannot be inline. So inside the function you have to say inline off. Okay, and then for the top function you use the data flow using the string. Okay, you declare that's the HLS string. Okay, and then the communication channel, you declare the string. You create the string, yeah, and then specify the data flow. Okay, so that's the standard way to describe a data flow function. Okay, so how do you do the data flow on loop? And we also introduced that before. Okay, so in here you have there's a one loop here, and there's a second loop here. Okay, and these two loops you want to run concurrently with the data flow. To do that, you have to meet those requirements. Yeah. First, those loop, this loop and this loop, the inner loop. Okay, there's a there's a must be very simple loop. Simple loop means there's a has to be constant bound, and also the index increment by one. Yeah, and the data flow pragma. Okay, data flow pragma is wait. The data flow pragma is inside the loop. Okay, this big loop. Okay, and and the inner loop, the most inner loop has to be pipeline. Okay, so this when you write the code, make sure you meet all the requirements here. And another thing is, if there's a function data flow, okay, then make sure you use the AP control now, because those kernel function does not trigger by the you don't use any of a handshake protocol on the block level, okay, because the function, the kernel function is triggered by data, okay. It's based on the availability of the data, so you don't use any block level protocol because nobody gonna to do the protocol for you, okay. Yeah, and then the process, uh, the for the data flow, each stage can execute different rate. That's okay, but in order to get the maximum performance, you try to balance the throughput, okay. Yeah, so that's when you design the function level data flow. Yeah, so that's the thing you need to take care. Okay, and there's a rule for data flow that I already explained in the lecture before. So yeah, I don't repeat it again here. Yeah. Okay, so this slide is very important. Yeah, so I hope you can fully understand the statement in this slide. Okay. This data flow usage techniques. First, I have repeatedly emphasized that separate read, compute, write. Okay, so for the I/O read-write, you string from or to the XI memory once. Okay, you only read the I/O once, so that you minimize the I/O read, and then you become a string. Okay, and all the compute kernels interface using the string. Okay, that's the canonical form that I just introduced. Okay, so but in your code, you may have repeated access data or irregular the access patterns. In this case, you use a small local cache for that. Yeah. Remember, in many of the image processing or convolutions, you we use the cache like a window for 1D, or use a line buffer. Remember, we use the line buffer for 2D the convolution. Okay, for those is for repeated access data. Okay, so that's the why I mean the local cache for that. Yeah, you use the local cache for those repeated access data paths, and also you use conditional branching. Okay, so if a data flow, for example, you cannot say use condition, and then there's a for loop here, else another for loop. Okay, this is really bad. You remember, the data flow cannot have a conditional. In here, there's one rule here. Okay, yeah, conditional execution task. That's not allowed. Okay, so in this case, you want for loop and put the if else here. Okay, so perform conditional branch inside the pipeline task rather than in conditional execute task. Okay, and we actually encourage you extensively use a conditional operator inside the loop because it does not impact the pipeline. Yeah. At last, yeah, you will impose using the HLS stream in the very beginning. In the very beginning, you simply define your data structure and interface using the HLS stream. which will enforce you to do a good coding practice. And then you have to think around using the right data structure, for example, here, to overcome the case that your algorithm that needs. Yeah. Once you put that in place, think around and try to overcome with various techniques, because only by doing that, that give you the most optimized performance and resource usage. Yeah. So that's the recommendation I give to you. Yeah. Okay, so let's take a break. I think we finished half of it. Yeah, I do need a break. Yeah. Okay, let's come back at 11:10. Okay, any questions? Is there any question? Yeah.
Hello，
Yeah. Okay.
老师，等一下
校长好。
能不能请教一个请教一个 string 的问题啊？
可以啊，可以啊，你讲。那
哦，您先休息一下，我等一下再问好了。
OK，好。哦，You are so considerate. Thank you. Okay. Yeah. Okay. So can you hear me?
Yeah.
Yeah. Okay. Yeah. So 浩腾，Yeah，没问题。
老师，我想请教一下，就是
好。
最近我们在看那个我们在看那个 fin，然
嗯
后为了要完整控制它的 I/O，所以我们先把那个它有一个 IODMA 先把它取代掉，然后接自己的东西。那如果 string 它怎么讲，在试的时候 deploy 下去，然后它停住了，有没有什么需要注意的？
按
有没有？
住了是吧？你在跑那个口信的时候是吧？跑什么分住？
应该是就是和好，然后放到 FPGA 上面。就是我现在在试，我现在在尝试观察 Fin 它合出来那个 NN 的那个 IP 的行为，
是。
然后
你可以做口
它那个
信吗？你可以做
啊，
口信吗？可不可
我是
以做口信？
先
你听得到吗？
哦，你是说在 Fin 把它合出来之前，
呃，有没有可能做口信？我想。
那我可能要我
哦，
先看一下，因为我现在是就
因为你
是把它
直接上了 FPGA 不好 debug，很多人看不见。
好，
你私信对，不太确定是不是能跑口信，
没有那我
可能
看一下能不
可能好像
能试。
不太好跑，我想想看。
然后有一
对，
点值得提，我
嗯嗯
觉得值得提一下的是，之前
嗯
做别的 lab 的时候，那个 string
嗯，
有别的讯号嘛，像那个什么 t last，
塞笨，对，塞一些 OK 呀，
那在 fin 合出来的这个 NNIP，它的 string 很
没有，
简单，
对啊，
那个 string 只有3个讯号，就是 data，然后还有 value 跟 ready，然后其他都没有。
对，这个就是 HLS string，unless you 你自己去specify 其他的塞笨信号，对啊，
好，所以我只
你可以
在想说有没
看那个
有可能跟这个差异有关？那个
不会，
不会。
呀，但 XIS 又不一样啊，XIS 就是 XI 的 protocol，它就有很多其他的 control 信号，
嗯，
但在 kernel 之间用的 HLS 那个 string，基本上就是 ready 跟那个 rest 啊，
那我想要再请教一个问题。那老师
啊
就想象你今天有个黑盒子，这个黑盒
啊
子你只知道它 input output 都是 string，然后你不知道这些 string 有多长。那
对啊，
如果我想要设计一个 IP，然后
嗯
这个 IP 是可以让我去观察 这个黑盒子的行为，而不会停住。那有没有什么需要注意的事情？
所以你要用 non-blocking 的 string 啊，否则的话那个 process 就在等 input 了。
Non-blocking string。
对啊，要用 non-blocking，所以你可以 check empty before 你再去读它。你也
好，
again 那个 textbook 里面也有谈到这个，你可以看一下，
好，
要用
我回去看一下。
non-blocking，对，要用 non-blocking，而且基本上你都要用 non-blocking，要不然写出来扣有点危险。
啊、
容易
因为
分组。
因为我之前就是有个地方，就是我在 wait，可是它 wait 它就一直
就停了。
它就没有反应。
对啊，对啊，对啊，
好，那
对啊，
我再看一下。
因为 data string 的 data 本来就会 store 的，你不能 guarantee 它 always 都来，所以它一定会 store。
嗯
store 你要能够 handle，那你不能那个 process 就横在那里了，在等 input，所以要用 non-blocking。先去看看有没有 data，看有没有 empty，不 empty 你才去读它。
嗯
或者 HS string 也有 provide 一个 non-blocking 的 read，对吧？
嗯。
它会给一个 flag 回来，说这个到底 read 的 data 是不是 valid，它会 return 回来，看是不是因为是 empty 的。
哎，那像这种 non-blocking 的也是适用在我刚刚说那个它 fin 的 string 只有 data 跟 valid 跟 ready，这个也
都可以啊，都
都可以。
适用啊，会啊，
哦，
一样一样。这个 HS string 就有提供 non-blocking 的那个 function 啊，
嗯，
你用那个 non-blocking 的 function。
好，我那个我再看一下 data sheet 还有 textbook 的东西。
对对，
好，谢
这样
谢。
OK 好。Okay, let's continue the latency. Okay, so I probably need to move faster. Yeah. So today lecture is a very heavy duty. Okay, that basically conclude all you learn from this semester. Okay, I probably will skip some details. Yeah, I will move faster. Yeah. Okay. First, latency. You can use the latency. That's a compiler. That's a program you can control the compiler. Okay. So it provide the min and max. Okay. So the minimum. So the compiler will try its best to optimize with given spec. Okay. And it's also for a loop. Okay, for a loop, you can specify the latency. For example, for this loop, you try to do the maximum 12 cycle latency. Yeah, and you can also group a signal if you want them to change within the same clock cycle by latency 0. Okay, so you probably write this code in a structured design method. Yeah, you specifically specify all those signal has has to be happen at the same time within the same cycle. Yeah. So I don't see how you can use that. Yeah. But I believe there's a you when you design something in a structured way that you may need a specific control on how and when the signal change. Okay, merge loop. We mentioned that for example, for this loop, okay, that's if it's a latency, iteration latency, and there's a number of data, and that's the II. So for these two loop, you take that much latency. But once you merge that, you get this much latency. So you reduce the latency. In addition to the benefit of latency, you also can do more efficient gate or larger optimization. Yeah. So that's a merge, a sequential loop, so that you reduce the latency. And that's a loop merge rules. I probably that has been introduced in the lecture before, so I don't repeat. Yeah. And then another thing is a flattened nested loop. Okay. So we all know that for nested loop, it takes one cycle latency to move between the loop. Okay, so for the loop with a small iteration count, this one cycle moving in out the loop is really actually introduce a lot of cycles. Yeah. So you want to flatten the loop. Okay, so become one loop. So you eliminate the inner loop entry and exit latency. Okay, so that's another technique, flatten the nested loop. And merge is for the sequential loop, and flatten is for nested loop. Okay, so to do the loop flatten, that we a lot of time we really want to construct a well formed loop. It give you a lot of benefits. Okay, what I mean by well formed loop is first there's a constant bound, and you try to increment by one. Okay, so try your best to form a loop with this kind of condition. Or use a perfect loop, because perfect or semi-perfect loop allows you to do the nested flatten, the loop flatten. And we also introduced the techniques how to turn imperfect loop into a perfect loop. For example, if there is a loop body between two loops, then this one should get merged into the inner loop. Okay, and in the midterm exam, there's a test for how to turn the imperfect loop into a perfect loop. Okay. Okay, next good practice is we try to place the if statement in the lowest possible scope in a nested loop. Okay, yeah. So we try to avoid placing loop within conditional statement. For example, this code, you have a conditional statement that's for two different loop. Yeah, and then you move the conditional statement inside the loop. Okay, move the conditional statement inside the loop. Yeah. So this uh, is good for the data flow and also good for the loop flatten. Yeah. And but this is a contradict to how you write the C code, write the coding for CPU, because in the CPU branch introduce a pipeline store. Okay, so if you write the code, this kind of code is not favored for the code for CPU, because for the for loop you always run into a branch. Okay, so introduce the pipeline store. So for CPU code, you will prefer coding in this way, because once you have a one branch, and then later on in this loop there is no branch. Yeah. Okay, so that's different from the how the code optimized for CPU. Okay, for HLS, yeah, put the if statement in lowest possible scope. Okay, keep this in mind. Okay, and then we should simplify the loop exit condition. Yeah, if you have a multiple exit, then try to merge into one. Okay, that give you a better merge. If you want to do the loop merge, okay, you should practice this. Yeah. Okay, this slide give you a summary for flatten and merge. You can see from this original code, you have a 36 transition. After applying you first apply loop flatten, okay, and then apply loop merge. Then you can get 18 from 36 to half of you do same amount of work, yeah, but you eliminate half of the overhead for doing the loop entry. Yeah. Okay. Okay, so that's I introduced various techniques to reduce the latency. Let's look at the area optimization. Yeah. So there are the following techniques for area optimization. I will go through them. Yeah. First, if you want to limit the resource usage, you can use the directive allocation. Okay. So this allocation, you can specify how many you want to use and the type of resource to use. For example, in here, this example, you have a full function call. So by default, you will instantiate four functions running in parallel. Okay. And then you can use the HLS allocation to limit using one function. So you can become this. And then the HLS will synthesize all the marking control logic for you. Okay. And then for this example, you can specify that's an operation. Yeah. In this, there's you use a fully enroll. Okay, fully enroll. However, you depend on your area requirement. You limit using 16 multiplication. Okay, so although fully enroll, suppose you will use 318 multiplications to do the fully enroll, but you impose another constraint to limit to 16, then the compiler will use only 16 multiplication. Yeah. So this give you a good handle to control how much resource you want to use. Okay. Furthermore, you can use a bind OP. That means you specify the type of operator you can use. For example, you try to use a multiplication with latency 2. Okay. And in here, I specify using the adder, but using the DSP. Okay. But if you write the code in this way, because in here, you specify the variable, okay? In this code, you need to isolate the operation you want to use. So you have to separate using introduce an intermediate variable so that you can specify that this variable is the latency 2. Okay, instead of the whole operation. Yeah. Okay, so that's how you can use the bind OP. And you can bind storage, basically the memory type you want to use. So you can explicitly specify what kind of a memory you want to use. FIFO. There's a different type of a memory, and then also you can use the block run, ultra run, what kind of the memory type. You use these two to control the resource to use. Okay. Another thing is you can reuse the hardware. For example, in here, if you write the code in this way, that it will instantiate three functions. Okay. So you can also use this way to use one function, use a for loop. As the previous, there is allocation. Yeah, that's another way that you can limit the number of functions to use. Yeah, so use the for loop, and then you will limit using only one function. Okay, and another directive you can use inline that give you better optimization because you remove normally the larger optimization. Okay, I'm not talking about HLS. I'm talking about the variable code generated by the HLS and then going through the logic synthesis. And the logic synthesis normally will not optimize across function boundary. Okay, so in order to get better logic synthesis optimization, you want to remove the function hierarchy. so that you can have a better larger optimization and get a better improve the area or even a better sharing or timing. Okay, so you use the inline. Okay, yeah, and for this one, use the allocation. Okay, and then the inline only apply to the function specified. That, for example, in here, you specify that's a top function. Uh, okay, and the location is full. Okay, uh, so under the top, but the full function is not under the full top. Okay, so you could not limit its usage. So when you synthesis, you get this result. You still have a two full function instantiate. Okay, so a better way to do that, you have to use an inline. Okay, you try to inline the dummy, so you make the full function goes up one function hierarchy. Okay, and then you can use the allocate. Yeah, in this case, that you will just use one full. I don't know whether you understand about this. Yeah, this is simply because the allocation has the scope. Yeah, yeah, limited. So since the full is under one level function, so it could not perform the allocation well. Okay, so that's some uh, precaution when using the inline. Yeah, another uh, pragma that can provide a more efficient resource using a function instantiate. As I said, that larger optimization could not optimize across function boundary. Yeah. However, a lot of time the this function could be further optimized depending on the input. If there is a constant input, then the constant input can propagate inside the function to do give you a better resource optimization. Okay. Yeah. So in that case, if you still want to do function hierarchy, but at the same time you want to optimize each function effectively, so you can use the function instantiate. So you can create a unique RTL implementation for each instance of function. Without this, the standard way is you have the same function implementation for all the invocation of a function. Okay, so every call of the function, you get the same, exactly the same implementation. Yeah, but in some cases, that you want to uniquely optimize the function, then you can use the function extension. For example, here, okay, for this function, it's called full stop 3 times. However, they have some input is a constant input. That's constant input, and the constant input can be propagated into the function. For example, +1 and +2 and +3 can give you different optimization for this function. Yeah. So in this case, you put this pragma so that whenever you call it, it create a unique instantiation of this function. So you get a better optimization. Okay, loop merge we have talked about. When you loop, you can do further optimization. Yeah. So here. Another technique is you have to use the data type wisely. Okay, so use arbitrary precision, and when the arbitrary precision is especially effective when you apply on the function argument, because the function argument that it will propagate into the hierarchy down the string. Yeah. So to reduce the resource, choose the data type with precision that's meet the target and don't use over the need. Okay, the next one is the array reshape. Uh, Last time we talked about array partition. Yeah, array partition will create a lot of memory block. Okay, so a more area efficient way is to use the array reshape. So you have a same block of memory, but with a wider bandwidth. Yeah. So that's another way to efficient use the memory block. Use the array reshape. Okay. And another way is wisely using the larger optimization. Okay. And you can use the operator pipeline and use the expression balance. Yeah. Okay. So it will give you a better larger, especially using the expression balance off. Yeah, to save the area. Yeah. So by default, for integer, the balance is default on. Okay. For floating point, the balance is default off. Okay. So actually expression balance is the default on. Okay, give you a better cycle latency. However, it consume more resource. Yeah. For this, they can sharing. Yeah, the resource. Yeah. So if you want to save area, then you should use the expression balance off. Okay. So how do we reduce the channel resource when using the data flow? Okay. So we try to use streaming because if you use a memory channel, then it will create ping pong buffers. So in that case, then we have to try to use the data flow memory channel carefully. Yeah. So we did better using the streaming. Okay, using the streaming that using the FIFO. And for small streaming, a lot of time the FIFO depth is equal 1. In that case, that we just using we will use just the registers. Yeah. So if you the producer consumer running at the same rate, okay, you can set the FIFO depth equal 1. Yeah. So if this stage has X-ray reduced to X-ray, that's you take a X amount of data and only produce one data output. Okay, in that case, then you should have an input FIFO with depth X. Otherwise, the system will hang. Okay, you can, yeah, easy to understand. Yeah. So if you have a block, take one piece of data and generate Y piece of data. Okay. In this case, that you should set the output FIFO with depth Y. Okay. Again, if you the depth is too small, then the system will hang. Okay. So you when design the data flow, you have to optimize the FIFO depth in order to reduce the area. Another subtle thing is you better declare the variable in the deepest scope possible. Okay. So the practice is when you write the code, for example, you have a for loop. Okay. And to reduce the resource, you declare the variable just before you use it in a loop. Okay. So if you have a multiple nested loop, okay, or you have a few sequential loop, okay, then you try to declare the variable, yeah, before use it, before the variable x, then you use the variable, okay. So the way you do that, you can save the area because you can minimize the data dependency and FPGA hardware resource simply because it does not need to preserve the variable data across loop, and those loops do not use the variable. Okay, for other loop, it does not use this variable. So you declare the variable here. Okay, then it has to preserve this variable. Yeah. So that give you the better resource sharing. Yeah. For example, if you have a piece of a resource, okay, the variable that's if it's an operator or it's a variable, it's a array or register. Okay, then you can actually this register can be shared by others. Yeah, if you put the variable in a wider scope, then you get less sharing for this resource. Yeah, and also the state, you have to keep the state. Yeah. Okay, so there's another guideline here. Yeah, you just declare the variable just before you use it. Yeah, so when you read the code, then you will see a lot of people just declare the variable just before use it. Yeah. Okay, they simply follow this guideline. Okay, last I will talk about host optimization. Yeah. So remember, in this course, the topic is application acceleration. Yeah, and a lot of students simply focus on HLS optimization and did not put the eyes on a larger scope on the application level. Yeah. And actually, the application performance often depend on the host, how you write the host code and how the host code interact with the kernel function. They often play uh, a much impact on the overall system performance. So, so I would like to emphasize the importance of a host optimization. Yeah. Okay, there are three areas that I like to address for the host optimization. First, we try to reduce the kernel enqueuing. That means kernel in, when you the number of times you call the function or trigger the function. Another very important and critical issue is how to optimize data movement. And how do you do the kernel scheduling? I think that these three things dominate the techniques of host optimization. Okay, let's first talk about how to reduce the overhead of a kernel enqueuing. Okay, first you have to recognize a fact that to dispatch a command and argument to kernel takes 30 microseconds to 60 microseconds, depends on how many arguments you want to pass to the kernel. So that's a very long latency. Yeah. So we need to really need to optimize the enqueue of the kernel code. Okay. So we need to minimize the code to the CL enqueue task. Okay. So it is better instead of a very small amount of data, we want to finish all the workload in a single code. Yeah. And then we want to aggregate large packets. So when you call a function, make sure you aggregate many small pieces of data into a big chunk of packet data, and then send to the kernel function. Okay. For this example, suppose in here you have a adder. Okay. Every time you call the adder function, you only call the size. Right now the size, for example, is 256. So every time you call this function, you only process 256 pieces of data. Okay. So so the better way is when you call the function, then you can give a batch number. So you use a for loop with a batch. For each batch, you process 256 piece of data. Okay. So in this case, if you write the kernel function in this way, you only need to call function, this kernel function once, instead of you have called that many times, number of batches. Okay. Yeah. So that's another technique. This one that's something that I mentioned in the course before, that we really like to have a kernel which is auto restart. So that's a free running. Yeah. So to do that, actually, we want the kernel start determined by availability of the data. So without the host program to include the task. Okay. So this kernel just continues running. As long as there is data fed into the kernel function, then the kernel start running. Yeah. For this, it's available in the newest release of Pratice tools. Yeah. And I will, for advanced project, that you should consider using the auto restart kernel. Yeah, they tell various means to do that. The basic approach is the host to kernel is using the stream interface. Yeah. So as you recall, for the kernel argument, if you use a string, you use the AP control none. Okay, so that means there is no block level protocol here. So it also means that the host doesn't need to control or synchronize this kernel code. Yeah, it just simply once they stream the data in and then start doing the computation. Yeah, so this is a very efficient way to do that, and you can reference this 1931. However, there has to be 2021.2 version. Yeah, look at this document. You will know how to do the auto restart kernel. Okay, here let's talk about how to do the optimization for the data movement. Yeah, first the OpenCL computation model we introduced. There are different levels of memory, from host memory to global memory on the FPGA side, and then you have an on-chip memory, and then reach the kernel to do the computation. Yeah. So there are different level of memory. So we try to maximize all level of memory interface. And in between the host memory and kernel memory, there is an I/O bus, which is PCIe. Oh, I didn't. I should put the PCIe here. Okay. So keep in mind when you want to do optimize for data movement, you have to maximize all level of memory interface. When you evaluate the performance, do look at each of the memory. For that's the system memory, and that's the DDR memory on the PGA. And you also need to observe observe the PCIe bus. So look at those bus utilization and see if there is any inefficiency there, and then you optimize. Yeah. And also, I recommend that you optimize data movement first before optimize computation. Yeah, that's why I want to emphasize this is oftentimes when you optimize the kernel and then you find out you could not reach the target throughput, and then you dig into it, then you find out, oh, the memory bandwidth is not optimized, and then you go back. Okay, so you keep a back and forth, optimize two different goals that really wasting time, wasting time. Yeah. So when you try to do the application acceleration from ground up, I would suggest the methodology is first you the kernel function, you don't spend too much time in optimize the kernel function. You simply make your kernel function as fast as possible. It doesn't need to be the real function. Okay? And so try to use the ideal kernel function performance, the best kernel function performance. Make a kernel function, for example, you simply read enough data in, and then you just do very simple operation and then output. Okay, and the latency is 1, and then yeah, those throughput is the maximum. Okay, so with this kind of code, first construct, and then you focus on the data movement. Okay, that's the first step. Yeah, and then so to do that, you separate the data movement scheduling from the computation kernel function. Yeah. At this stage, so you can focus on the data movement. Yeah. So this a flow recommended by the Xilinx that so that's the target. Yeah. First, you run the software simulation. Software simulation. First, make sure the function is correct. But in this stage, as I said, the kernel function could be a very ideal one or fake one. Even it's fake one, a very simple operation. It doesn't perform the actual function. Yeah, simply to make the. But however, the I/O is correct. You need to provide the correct I/O, and you will generate the output. Yeah, and then you run the hardware emulation. Okay, in the hardware emulation, then you can analyze from also the report from the kernel compilation, and then study the report. Okay, and look at the profile, timeline, and all the trace. Then you try to optimize it. So you try to iterate it this way. Okay. To in this stage, you only optimize for the data movement. Okay, and then you put the kernel function into the FPGA to do the real hardware running. And then when it's because when you do the kernel optimization, when you do this code simulation, it doesn't give you correct DDR or PCIe latency. The latency is fake. It doesn't give you real latency, but just give you you can get the idea how do you do the out of order and the pipelining. That will be correct. But the latency shows in the code simulation is not exact because the DDR and PCIe is not running with the actual hardware. It's run with the simulation model, and it's not the real things. Okay, so to do the true evaluation on the performance, you have to put into a PGA running in the system. At this time, you have to turn on the profiling. So when you run the actual application and then you study the profiling result. Okay, then you do the optimization again. So there are two-step optimization. One is a code simulation, okay, and this one give you good handle on the pipeline and scheduling, okay, but latency is not accurate. And you do the actual hardware, give you the accurate full system latency and performance. Okay, I hope you get my point. Yeah. First, yeah, focus on data movement. Yeah. Okay, for host program, one important target is you try to overlay data transfer with kernel computation. That's one example. Okay. If you put into an in order queue that for the data movement and kernel function that you will do the non-pipeline and in a sequential way. Okay, that's what you get. Okay, so if you use out of all the command queue, then you will focus two things. Okay, then in here you try to maximize the FPGA computation utilization. You see, in here the kernel function, there are a lot of idle time here. Then you try to pipeline them so that to increase the FPGA computation utilization. And also, if this is a PCIe bus or the DDR memory, you can see you also increase the data transfer on the IO bus or DDR memory bus utilization. Okay. And this is also important task, important thing here. Okay. Uh, suppose you want to transfer a big block of data. Okay, you have to move that big chunk of data before the FPGA computation can start. Okay, and then you move the data. Okay, so another optimization is you try to partition the big chunk of data into small one. Okay, once this one finish, then you can do the compute. This one finish, you can do the compute. Okay, so you can actually reduce the latency. Okay, it's very much like a data flow, right? Yeah, but you actually manually partition the data. Yeah, big chunk into small. This can reduce the latency. And you want to use the out of order command queue with event objects. Okay, like this. Yeah. And for this one, you use a double buffering. Yeah, use a double buffering. So when you doing one operation, then you can use another buffer to transfer the data for the next operation. So that you need a double buffering technique. Yeah. And also you want to balance the I/O and compute throughput. Okay. So there is you don't need to overdo one thing. Yeah. For example, you maximize the data movement, but you keep increase the data memory throughput. However, the computation could not take that much data. So for those memory throughput optimization has no use, and you also waste the resource for example, for the data buffering. Yeah. Again, if the memory data could not supply enough data to do the computation, then there is no need you need that much parallelism on the kernel function. So always balance the I/O and compute throughput. Yeah. And for this out of order command queue in lab 3, you have done that before, so you know how to use the event object to do the out of order command scheduling. Okay. Another issue is buffer memory segmentation. That's a very much that's a system issues. Yeah, we all know that the OS, the system memory, due to many process allocate the system memory, then the buffer allocation will create the memory fragmentation. Yeah, but to efficient transfer data to the kernel function, it's better using a big chunk, a continuous buffer. Okay, if the data are scattered, you either need to gather the data into a big buffer, or you use a gather DMA. Yeah, in the Xilinx provide QDMA, that's a gather DMA. That means the DMA can allow you to train a sequence of a descriptor. Okay, each descriptor point to different part of the memory. Okay, so you provide this a chain of a descriptor to point to the scattered data buffer in system memory. So you can do the transfer like a continuous big chunk of a data buffer. However, you need to prepare those those descriptor. That's one thing. Also, every time you allocate this memory, uh, you trap into the OS, so it's not very efficient. So often, if you look detail on the profile of the system running, sometimes you will observe the kernel execution stall. You don't know for what reason the kernel execution simply stall for long time, Yeah. So in that case, sometimes it's because it is waiting for continuous space to be free by OS, and OS doing the garbage collection is very time consuming. Yeah. Yeah. So if you observe this situation, that you know you need to allocate the device buffer and reuse it. So in order you don't want to always to do the memory management and doing the garbage collection. So you want to create, you allocate a big chunk of memory. You access a big chunk of memory from OS, and then you manage your buffer by yourself. So that's the Intel DK use these techniques. Yeah. So he knows his application, the characteristic of a buffer usage of the application. So it can adapt the needs of its application. So it provides a much memory management. Okay, so I just bring up this, bring your attention. This is an issue when you really do the system optimization. Okay, here, as we talk about, we have two kind of parallelism. One is the data parallelism. Another is the task parallelism. For software to control data parallelism, for example, the application has those functions. However, those functions actually working on different data sets. Okay, so you can have these three functions. If you run in CPU, it has to run in sequentially. So if you move to FPGA, you can have those three functions running in parallel. Okay, so in FPGA, you can create multiple instances of the same application, the accelerator, so that it can run in parallel. Okay, yeah, that's one technique for data parallelism. Or another case, the application actually run three functions sequentially, yeah, and these things are repeated, yeah. So it's repeating the sequence of function call, okay. And so you can imagine that in HLS, if you have a three function running sequentially, you can using data flow, right? Yeah. So the same thing, you put these three function, okay, put into three kernel, okay. There are three kernel for each function, and can use run the three function. Actually, in here, that's in pipeline, yeah, in FPGA pipeline, okay. So in this case, you can run the accelerator SQ in a pipeline and overlap fashion. Okay. For this one, you can see. So for each function, each kernel function, the FPGA resource is fully utilized. Not actually, there is no idle time in the FPGA kernel function. Yeah, that's the target. Yeah. So how do you do this kind of scheduling by the host software? Okay. Yeah. So for each of these three kernel, you can use the data flow or using the pipeline, and you can also apply the instruction level parallelism. Okay. Another thing is for those data move across the kernel function, make sure don't write the data to the global memory. Yeah, we try to minimize. The best thing is that we use a string, right? Use string to communicate or move data across different kernel functions. Yeah. And if it's using a string, then the host does not need to program the kernel. In here, if use a traditional way, that each kernel function still needs a block level protocol. Then the CPU have to use the in-queue task, and it's a very time consuming and take up a lot of CPU time. Yeah. So for this is still a traditional way, yeah, to do that. For each kernel function, you trigger that. Yeah. Okay. But the problem, this one you trigger each function that it has to wait for data. Yeah. So like the function two is only depend on the data. Hmm. So it should use the data flow, and those functions should not have a block level control. So I'm saying something here is in here you cannot trigger this function because data is not ready here. Yeah, this one is corresponding to this function. Yeah. So for this drawing to achieve this, you have to use the data flow. You have to use the data flow in order to do that because the data produced it fit into function two. The function two start running, and function two does not need to wait for the. It should not have the block level protocol. That means you don't need the API to invoke that. Yeah. So for doing that, I will say the host does not need to program the kernel. So for each kernel should use the data flow with the AP control now as a block level protocol. Yeah, and then we can use the auto restart kernel to save the host API code. Yeah. Okay. So I think that's a very optimistic or very high level host programming. Yeah. I hope you one day have the capability to develop a system like this. Yeah. Okay. It's durable. Yeah. So you can find a project to really exercise this test level parallelism from the host code. Okay. So this is my last slide. Yeah. So for kernel scheduling for multiple compute units with of the order, there are two methods. There are two methods. Okay, one is for each kernel function, for each this compute unit, you create an in order execution buffer, the command queue. Create two command queue. Okay, so for these two command queue, when they schedule those commands, since it's in order queue, so the command in the same command queue will execute in sequence. However, the two independent command queue can execute out of order. Okay, that's one thing that you create command queue, each command queue for each compute unit, or you can have multiple command compute units share one command queue, but that one command queue has to be out of order command queue. Otherwise, the system will be deadlocked. Okay, or unnecessary store by other compute unit because those two compute unit may actually different pace. Okay, and you put the command of the two command queue into one queue. This queue has to be out of order command queue. Okay, yeah. So you are two methods to manage multiple command units. Yeah, and what Xilinx suggests is use this scheme using a single out of order command queue and manage the event dependency and synchronization, instead of using multiple command queue. Yeah, I think this will consume less resource and a better system schedule because if multiple command queue and if you run concurrently, then there is an overhead to switch between different command queue. There may be a different context and there's an overhead involved. Yeah. So it's better to use a single command queue, but it's out of order command queue. Yeah. So that's the scheme Xilinx recommend. Yeah. Okay. So this slide conclude the host optimization. Yeah. Okay. So in today, the topics actually is quite heavy duties. I believe it's hard for you to absorb all the materials. Yeah, but keep in mind, in the future, if you work on something complicated at the system levels, you can come back to refresh some of the idea here. Okay. Yeah. So, is there any questions? Yeah, I'm open questions. Okay. Okay. So after this lecture, we will have 2 weeks, and on I think January 17th, we have the final lectures. There are some open issues that I didn't address in this lecture. It will be covered in next lecture. Yeah, and I hope you do the final project. You can all deliver very successful final project. Yeah. Okay. So okay. Okay, if there's no question, so we will conclude today's class. Yeah. Okay, so see you in 2 weeks. Yeah. Okay.